Hello class, this is Professor Feynman. So in part 2 of the introductory lecture, I want to go over just some illustrative examples to go with the definitions that we covered in part 1. And so here I have a scatter plot. So this is a bivariate problem where we have the x-axis is from 0 to 1, so this is a normalized, we don't know what x is for this example, and then we have y in arbitrary units, in an arbitrary scale going from 0 to about 10. And so we have some data points plotted here. So this could be the output of a computer simulation, or maybe these might actually be measurements that were actually taken either in an experiment in a laboratory or out in the field. And so let's go over some linear model examples. And so whenever we have a plot like this with our data, our independent variable and our dependent variable, we want to perform regression on this data set and find the underlying functional form. And so first, if we just look at this data, the simplest model that we can assume is just a constant. And by just looking, we can sort of, let's just draw a straight line kind of through the data. And so this line would be y equals, I'm going to call it beta naught, where beta naught is some constant. And this, if we were actually performing linear regression, this would be the sample mean. And so here, these data points, we have a population. We have a population of data points. And so the most basic linear model that we could assume is y, our variable y equals some constant beta naught. And generally, we would set that equal to the mean value of y of our data points. And so it actually, just by looking at this data set, this y equals a constant actually might be a good model, okay? So we don't really know. Now, so this y equals a constant, so y equals a constant, we call this is a zeroth order model, okay? A zeroth order model. So the next thing, which is really common, is let's draw a line of best fit. And so here, maybe it's hard to tell without actually performing the regression, maybe there's a relationship like this. And we would say, this equation would be y equals beta naught plus beta 1 times x. So it's a simple linear model, or this is a first order polynomial. A first order polynomial or a line of best fit. And of course, this particular line, it has a negative correlation. But also maybe we would have gotten a positive correlation. Okay? And so maybe and so here, for this line, beta 1 would have a negative sign. And so here we would also have y equals some beta naught plus beta 1x. So this line has a positive correlation. And so in some fields, so for example, especially in social sciences like psychology, sociology, and even a lot of the medical research, many researchers are just looking for basic correlations. So is there a positive correlation between variable x and variable y, or is there a negative correlation between variable x and variable y? And so a lot of regressions are just looking at, is there a correlation or is there no correlation? Also, we could also do if we look at this, we could also try to fit, for example, let's say a quadratic. And so here I'm just once again, I'm just using called eyeballing. So let's maybe I could try to fit a quadratic curve, something like this. Okay? And there would be an equation for this line, y equals beta naught plus beta 1 times x plus beta 2 times x squared. So this would be a quadratic model. This would be a quadratic model or a second order polynomial or quadratic. And so here are some of the more, simple options, and we could keep doing this. We could keep adding other model details. Okay, and so this would be probably, especially for a bivariate case like this. These are some of the models, regression models we would build. We would start just doing simple, what are called polynomial fits. But you should always remember though. Maybe there is no relationship. Maybe this is just random noise in the data. In this example, we don't know. And so you should always remember that the y equals a constant, which is generally would be the sample mean, is sometimes actually the correct model in some circumstances. Okay, so I'm going to give you a minute to write all of this down, and then we will erase and go to the next slide. And so here in this example, we don't know anything about x and y. We don't even know what those variables are. Well, so now I'm going to give a more detailed example. Yeah, and so in the absence of other information about your variables x and y, generally we will do low order polynomial fits. Those are sort of the default options for regression models if we don't have any other information. And so here I'm presenting the same data set, but I'm going to provide you with something a little bit more information. So now let's pretend that the x-axis is actually time, and the unit of 1 equals 48 hours, or 2 days. And then the y-axis here is the temperature, and the y-axis is the temperature, but it's in degrees Fahrenheit. And so, for example, the United States uses the English system. And so and I'm from the United States, so for temperature outside, I usually use Fahrenheit. But it's the degrees Fahrenheit divided by 10. So this would go from 0 degrees Fahrenheit to about 100 degrees Fahrenheit. And so 100 degrees Fahrenheit, that would be approximately maybe 34 degrees Celsius. And then 32 degrees Fahrenheit is freezing, is 0 degrees C. And so let's conceptualize that this data is actually temperature measurements that were performed over a 2-day period. And this was performed at a weather station, where I'm showing here in this picture, and high up in a mountain in a high northern latitude during the summertime, maybe let's say in July. And actually, I personally have spent several summers in Alaska, and I've done mountain hiking. I've hiked on mountains like these in July, and I have personally, with the backpack and going camping, doing the mountain climbing and the backpacking, and I have personally experienced within a 1 to 2 day period going from below freezing temperatures to very hot temperatures above 30 degrees Celsius. This can actually occur in a situation like this. So this is actually somewhat realistic. And so here, when we have additional information about our variables, here now we might want to think about what other information can we add to the model? Okay, but this should be a linear model. And so one thing we know is, and this is obviously showing the temperature goes up and goes down, and goes up again and goes down. So there's night and day. And so sort of on the a 12-hour period, you should get some large shifts. So the one thing we might want to try to do is, what about fitting a sine wave? And so I'm going to just try to, I'm just going to like roughly try to draw one here. Okay, so maybe I'll draw a little thicker. Here, let me use black. So let's draw in sort of a rough sine wave. And so now we would need to come up with an equation for this line, and usually we would learn, so this would be y equals, now it would probably be some constant, and let's call this approximately 50, so maybe 50 degrees Fahrenheit plus, and kind of just from this graph, we can judge the amplitude. What is the amplitude here? So going from about 50 to about 80, that's about 30. Yeah, from 50 to 20. So plus 30 sine of, now let's do pi divided, now this, let's see. So 0.5 is 24 hours is a full cycle. So maybe pi divided by 24 times t. So this, our x-axis is now actually not x anymore, it's time t in hours. And so here, this might be just by, and once again, we're not actually performing the regression, but just by, with our eyes fitting a curve, this might be a reasonable model if this is actually the true data set. It was collected at this mountain weather station in July in a mountain in the high northern latitudes. And so the general equation for this line might be beta naught plus beta 1 times the sine. And here we are assuming, because we know this is environmental temperature measurements, we know because of night and day, it's on this 24-hour period. So this is the frequency. Pi divided by 24 is the frequency. And so here we're actually hardwiring in the frequency. And so this is what we call, this is a linear model. Now there's a nonlinear function sine, but it's the regression. If we actually would perform the least squares regression, we would find the optimal value of beta naught. Here I said it's approximately 50 and maybe approximately 30 degrees Fahrenheit but like here the regression would actually learn the optimal values of beta naught, which is essentially would be the y-intercept here, okay? And then this beta 1, the amplitude of the sine wave. And so the regression would find the optimal values of beta naught, beta 1, given this particular data set. And so we call this is a linear model because it's a linear combination of the coefficients. Beta naught plus this beta 1, and beta 1 is times some function of x or some function of time in this case. It happens to be a nonlinear function of time, but the coefficients, it's a linear combination of the coefficients. That's why we call it a linear model. Okay? And so that's so this is some of the things. So in the previous slide, we didn't have any information about what was the physical data points. What was the x and y? What were those variables? And so, but if we do have information about the underlying physics, you can incorporate that knowledge into your regression model. So yeah, so if we knew this was a temperature measurement, we would probably want to use some sort of sine function to capture the natural, that cyclical variation with time. Okay, so let me erase that. Okay, now let's do another example. This time we're going to do the nonlinear model. And so when we just visualize this data, we can sort of see that there's definitely some noise in the data. There's some fluctuations. And so we might want to, once again, use the sine waves. So this is actually similar to the Fourier series expansions. And so we might want to fit, there's probably some sort of underlying sinusoidal relationship, but then they're at higher frequencies. There also might be some other, smaller variations at a higher frequency. And so when we combine these two models, we might get something like y equals, once again, some beta naught plus beta 1 sine. But this time, I'm going to put one of our fitting parameters, beta, inside the sine function. And here we're using our axis x again, because we don't know what this data is. And then plus, let's call it beta 3 times sine of beta 3 times x. Okay? And so, in this example, this is a nonlinear model because our fitting coefficients, beta naught, beta 1, and beta 3, those are linear combinations, or this should be beta 4. But if we want the regression, in the previous example, we assumed the frequency was pi divided by 24, because we know there's 24 hours in a day. And so here, if we want the regression to learn the optimal frequencies of our two sine waves, the parameters beta 2 and beta 4 are inside the nonlinear function. And so this model is a nonlinear model because the fitting coefficients, which are learned or determined or estimated by the regression, these parameters are inside a nonlinear function. So it's no longer just a linear combination of fitting parameters. And so that would be an example of the supersupposition of sine waves is an example of and if you're estimating the frequency of those sine waves with the regression, then this would be a non-linear model. Yeah, so that's what we mean by non-linear model. And so we'll go over this in more detail throughout the course. But part of this exercise is just to see how there are many different options when we've collected we have this data set. As the analyst, you have many options of should we go for a very complicated nonlinear model or just y equals some constant. It's a very simple model, but it might be the most accurate. Before class, I actually generated this data set. This was a computer-generated data set. I think it was y equals some constant, maybe 5 plus, 0.1 times x, so there was a small linear term, plus, I think it was sine of pi x, plus, I forget plus some random noise. And this random noise was normally distributed with mean 0 and a variance of, I think a variance of 0.75. And so it was actually a linear, it was a small positive. So the underlying function, I actually generated this data set in MATLAB. So there was a small positive trend, plus then a sine function, plus then random noise. It was normally distributed with a mean 0 and variance of 0.75. So I think that's how I generated this data set. And so actually, none of the models that I showed was the correct model, because we actually had this, there was a small positive linear component.